Yep.
Yep.
Okay. So I2C stands for inter-IC. This is one of the most important serial protocols that you will encounter in your work, projects in the future. And also we're going to use I2C protocol in our second lab. So I2C is originally designed by Philips to enable inter-IC communication using a minimal number of pins. In particular, we use 2 pins for communicating using I2C protocols, besides power and ground. Using I2C, we can build a very simple universal bus for different ICs from different vendors. The hardware specification of this protocol is very simple. Even if you implement it in software, it's still possible. The operation speed of the bus is at 100 kilobits per second or 400 kilobits per second for most of the ICs. For newer ones, they can support 3.4 megabits per second. Now, this is not very high speed, but for most of the ICs that you will work with in embedded system domain, these data rates are sufficient. Yes, I2C protocol has a few great features. There are no special wiring or connectors needed. You have 2 lines. One is called serial data, denoted as SDA. The other line is serial clock, denoted as SCL. And each device on this I2C bus has its own unique address, and it's software addressable. So you can use your program to select different devices that you can talk to or you want to talk to. It supports master-slave relationship and possibly have multiple masters. It does serial transfer, as we mentioned earlier. Every transfer takes transfer 1 bit, and overall you can transfer 8 bit during one transaction. You can do bidirectional data transfer. So let's say you have a master and you have a slave. You can write from the master to the slave, or read from the slave device to the master device using the same 2 wires. And the max bus capacity, yes, 400 picofarad. There are several serial bus standards or protocols. UART was the one we talked about earlier, and SPI and I2C are also popular protocols, especially in modern embedded system design. There are CAN devices, control area network, and also USB. USB is very popular, of course, not only in embedded domain, but also in very general purpose situations. This table just qualitatively compare these protocols, and these are some rough comparisons, and they are not very quantitative, but you can get a sense which protocols are popular and why. So the software that involved in I2C protocol is basically using simple messages generated from microcontrollers to convey information on address and data. And devices often have complete interfaces, which means that when you work with I2C devices, if that device supports I2C protocol, it will be able to generate these signals from the hardware itself. We will see the timing diagrams later, or illustrations of the two wires, how they transfer data and address values. But most of the time, you don't have to write software to generate individual clock signal. Rather, you will use the control registers or other registers of the I2C device to send in, necessary information out or receive data back. The general procedure for communication. So we have generally a master device and several slave devices. You can have the master to talk to any one of these slave devices one by one, not at the same time. The reason being that this is still a bus, so you cannot have more than one people talk at the same time. Otherwise, there will be a lot of interference, and you won't be able to tell which signal is the valid signal. So the first step is to wait until I2C bus is free. Now, the indication of the bus is free is when both SDA and SCL are high. And we'll see some illustrations later. And after that, if one side, especially master, is trying to communicate, it will put a start message on the bus to claim the bus. And that's the one step that the master will claim the bus and be able to have other ICs ready to listen. It will then put a clock signal on the SCL line for others as reference time. And because it's a bus, so this SCL line can be seen by all the other ICs which are now listening. And the data on the SDA wire must be valid when SCL switching from low to high. And we'll see some illustrations and I'll explain further. There are two steps. Well, one important step is first we need to put binary address in series to identify target IC. You can connect multiple ICs on the same I2C bus, and which is often the case. But each of these ICs has its own unique address. It could be a 7-bit address, or in the later specification, you can have a 10-bit address. But most of the time, you have a 7-bit address to identify the device. Then you need to put some indication to identify the direction of the transfer. And this is talking from the master side. Is it sending or is it receiving? And then after that, the master will require other ICs to acknowledge the address and the readiness to transfer. And after that, the actual transfer happens. This can be 8-bit data after receiving ACK. And when we see 8-bit data, this data can be interpreted by the slave as addresses, if that's the case. If the slave IC is trying to look into some of its own internal registers, then it has to use some address. And this transfer could happen, multiple transactions. And at the very end, the master will send a stop message to free up the bus. So these descriptions could be very confusing, but we'll see some illustration very soon. Hopefully you understand this better. Now, we said earlier that the master needs to send out the address. The way to identify a I2C device is to use an address. The address, generally, it's 7-bit address. And every device that you connect onto the same I2C bus has to have different address from other ones. Otherwise, you'll be confusing yourself. This means that if you connect the same type of IC on the same bus, you need to have a way to differentiate these two, especially they are from the same vendor. Now, the question could be, how do we know the address? if I just purchase I2C device, when you purchase I2C device, like the accelerometer that we're going to work with, MPU 6050, by design, the vendor has assigned a unique address in this chip. So you don't get to choose the address. It's the address, it's the device itself has a built-in address. So you have to make sure that you are not using the same address on the same bus for different devices. Devices with master capability can identify themselves. This is, for some cases, you can do that. Again, only one pair of devices can have a data transfer session at a time because this is still a bus. You cannot have more than two persons talking at the same time. This is the hardware architecture, essentially a simple schematic how we possibly connect I2C devices. We don't show the power and ground, but besides those, we have this SCL and data line, SCL and SDA. We only need these two lines. We often have multiple I2C devices, so you can have this one, and other ones. All these I2C devices connect to these two wires. So each of them has a separate SDA and separate SCL pin that will be connected to this bus. On this bus, there's also pull-up resistors, typically 2K or 10K ohm. And there's VDD to supply the power to the system. And for each of the I2C device, they use those open collector design so that it can effectively isolate itself from the bus if necessary. And we look into this open collector design when we talk about the I/O pins. So this is essentially the same. On the input side, we can use this other circuitry to receive information from the bus. This is another example where we have this I2C bus, and we have a few things on the device, on the bus. We have a microcontroller, which is function as a master. We have 3 I2C devices function as slave. We have double EEPROM. This is a read-only memory. We have a temperature sensor, and we have a LCD controller. So all these 4 components are connected to the bus, and only the master will be able to initiate the transfer. There are certain signal patterns that are important for having this I2C protocol to work. We mentioned earlier that the very basic status for the bus is to be in the idle state. When in the idle state, both of these 2 wires are going to be logically high. So you see here, this means this is before this point, there's the bus is in idle state. And then at some point, the master will pull this SDA line to low, okay, as we see here. This is an indication that the master is going to start doing the communication. So this is what we call the start condition. So again, the start condition begins when both of the wires have a status as high. So that means the bus is idle, and the master drives this SDA line to low, indicating it's going to start doing the transfer. And after that, the master will start generating the clock signals. You can imagine that each of this square box is half of the cycle, so we can have a clock signal going like this pattern until it stops. And speaking of the stop, so this is the counterpart of the start condition. This is the stop condition. So the clock signal will be maintaining high, and which means the clock pulses have been stopped. And then this SDA is pulled up, so the voltage level from 0 becomes 1. And then this is an indication that the master device stopped the transfer. So the communication protocol just finishes here. So what's more interesting is what happens between the start and the stop. Between the start and stop, what we really need to do is to sending zeros or ones between these two devices. So what we have here is a pattern for sending signal or a value 0. This is the clock coming from the master. Okay, so you can see this is kind of 1/2 of the clock cycles. In the lower half, or when the clock signal is low, this is the moment the sender can change the value on SDA. When the clock is high, this is the moment that the value on the SDA should maintain solid or valid. So if the sender wants to change the value that will be sent out, it has to change during this half of the cycle, so that when the clock signal is low, where when the clock signal is high, this half of the cycle, this is when the sender has to maintain the value. And in this case, it maintains 0, so that's when we send out a 0. And the other case, as we shown here, when the clock signal is low, the sender changes the value and changes to 1. So when the clock is high, this is the value going to be sent out. So this will be the case we send out a 1. Okay, now we have the basic components of the transfer. We know the start, we know the stop, and we know how to send 0s and 1s. Now, when the actual communication happens, the sender and receiver will work in tandem and following this kind of pattern. So as we show in this example here, we have a start condition, okay, because we start with idle and then the SDA port is low, so the clock starts. And then the first cycle that we going to be sending out is a bit A6, and then A5, and another cycle A4, all the way to A0. And you notice that this is again the timing diagram. So you see this double lines in parallel, this indicating the data is valid. And then here we use this A6, A5, A0. We have 7 bits here. These 7 bits are the address, represent the address of the target IC that the sender is trying to communicate to. So whoever here has that address will should respond. So if we have, let's say, 0, 0, all the way 0, except this bit is a 1. So if we have these 7 bits, 0, 0, 0, all the way until the last, until the very least significant bit, this is a 1. So can you tell me which one of these ICs should respond?
The EEPROM?
That's right. So the EEPROM should respond because that's its address, 1. So if this EEPROM is connected properly and it's functioning as normal, it should respond. But before it responds, there's one more bit we need to send out from the sender. That's this read and write. Because based on this value here, we will know, well, the servant will know what kind of operation this master is trying to do. So up to this point, we have the 7-bit address, we have read-write indication. Then the next thing should happen is for the servant to acknowledge that. And this is the acknowledge bit. So the servant should put a 0 here to acknowledge that. And then what follows will be the next 8-bit. Now the next 8-bit could be data. So like we show here, we have D8, actually this should be D7, D6 up to D0, so 8 bits coming out from the next sequence of clock pulses. And once these 8 bits are received by the sender, or received by the receiver should acknowledge. So which means it's going to be polling the data bit to 0 to acknowledge that. This is another case why we use logic high on both wires to indicate that's a idle status. Simply because we use this 0 to indicating the acknowledgement. And then after that, we'll stop the pulse, and we will return this SDA line to high, so we end up having a stop condition, and so this whole transaction finishes. I have to mention that in many situations, this kind of transfer could go on for multiple transactions. So not only first byte, could be second byte, could be third byte, and so on. Depends on the actual chip you talk to. But every transaction, you can expect that there will be 8 bits with followed by an acknowledgement, another 8 bits followed by an acknowledgement. Okay, this is another example. We have, you see there's a message in the chat window. Okay, good question. What is the difference between servant and a receiver? Let me go back to the previous slide. Oh, what did I do? Okay. So we list here master and servant, and multiple servants, in fact. The intention here is to say, on this bus, there's only one of them, or should be one of them, control the whole thing. So that's what we call the master. And so the master will generate such clock signals to drive the data transfer. And servant will respond by acknowledging the address by maybe sending the data. But is servant always a receiver, or is servant always a sender? The answer is no. Because when we say sender and receiver, we're talking from the data transfer perspective, where the data goes from where to where. So we say that the data goes from the sender to the receiver. So if we're reading, let's say the microcontroller reads from EEPROM, so who is the sender in this case?
The EEPROM?
That's right. So the EEPROM is the sender because we read data from this device to the microcontroller. Now, in another case, if we want to control the LCD controller, so we're going to be writing some control information from the microcontroller to the LCD controller. In that case, what is the role of this LCD controller in terms of sending or sender and receiver?
LCD is the receiver?
That's right. So LCD is the receiver. So sender and receiver are really talking about from data transfer direction perspective, whereas master and servant is to say who's driving the clock. Yeah, it's a very good question. When we look at these I2C devices, some of them can only be read. For example, this EEPROM, you expect only reading data from this device. Also, for the temperature sensor, you read data from it. But there could be other I2C devices. You do both read and write. So let me move on to the next slide. This is another example. So we have quite a few I2C devices on this bus. We have pull-up resistors. We have microcontroller, which is the master. We have I/O. We have ADDA. We have LCD RTC, another microcontroller, and we have this EEPROM. Now, this EEPROM, as you can see, that we have these SCL and SDA connected to it. So these are the two wires required for I2C bus. In addition, we have a few extra pins that are specific to this EEPROM. We have A2, we have A1, and A0. It's interesting that you see, for this EEPROM, we have extra pins. And if you read the data sheet of the accelerometer that we're going to use, MPU 6050, you will find there's one extra pin instead. Now, the reason being, for this EEPROM devices, they could be from the same vendor. Let's say the vendor assigned the first 4-bit for forming these 7-bit address. And the vendor purposely leave these 3 bits open or configurable. And these 3 bits in the address is determined by how you connect these 3 physical pins coming from the chip. So in this case, the way we connect to it, this is the VCC. Can you tell me what is the 7-bit address of the EEPROM chip?
Zero 1 1. Oh no, 1 1 0.
Okay, so well, I guess you're right, depending on how you read it. So so you have A2 because it's grounded, so this value should be a 0, and this is 1, this is 1. So in fact, this is the exact address that will be assigned to this chip. Now, why do we do this? Why can't we just assign the 7-bit and that's it?
That wastes space.
That could be a reason. But think about when you have multiple EEPROM chip from the same vendor, can you connect 2 of them on the same I2C bus?
No.
You cannot, because if you connect the same chip with all these 7-bit address fixed, then you're going to cause conflict. So the 2 of these EEPROM chip will not be able to respond correctly. So the reason behind this hardware selectable address is to be able to have multiple such chips put onto the same I2C bus. Not every I2C devices do that, but some of them do, especially these EEPROM chips, so that you can expand the capacity of these chips. I'm gonna skip this. This is just some different addressing mode for 7-bit versus 10-bit. It's a bit more complicated. As we mentioned earlier, the bus communication on the I2C is using 80-bit byte. Each byte of transfer is acknowledged with the 9th data bit generated by the receiver. And apart from the start and stop, no device is allowed to change the state of the SDA bus. There's one line missing here, while the clock signal is high. Because the clock signal is high, that's where we expect to have a valid data bit on the SDA line. Multiple masters can compete, but only one could win the bus, so it becomes the final master. And there's no minimal clock speed. It really depends on how quickly or how slowly the master generates the IC, the clock signal. Also, the slower ICs can hold the SCL low. So if you hold the SCL low, that means you have to wait until the SCL, the clock line, become high to be able to read data. So this is a way to slow down the bus. That's called the clock stretching. So here's some example of doing single read or single write. There's one message from the chat. Is microcontroller always the master and device is always the servant? I would say so. Master is always the one who is capable of initiating the data transfer. So yeah, microcontroller is always the master. Okay, so this is to write to the slave device. We will start the transaction with the start condition or start bit. And then we send out the slave address and we send out a 0. W bar, this is to say that write operation is active low. So when you have a 0, that means that's a write operation. So whoever has this address, okay, should acknowledge, saying that, okay, I'm ready, so send me something, because from the master, it's gonna send some data, and then follows the data, the actual data coming from the sender to the receiver. And once that's done, so the device will acknowledge, maybe another piece of data, acknowledge, and P is the pause that we can just temporarily stretch the clock. And then for read, you can do read from a slave device like this. You will send out the slave address, and then you follow that by using a 1, 1 indicating it's a read operation. And then the acknowledge will be from the slave device, and the slave device will start putting the data out on the bus, because remember the master is trying to read, so the slave device will be putting data on it on a one bit after bit, and the master device will acknowledge after reading the byte, another byte, and then acknowledge again. The last one could be just right before the, actually, sorry, this P is stop here. It's not clock stretching. And master is the master transmitter, then the master receiver, and it transmits clocks all the time. It sends the address, a slave address, and then becomes the receiver for the case of this read. Here are some more complicated case. We have combine read and write. And you can read this. Well, let me explain a little bit. So let's say the combine write and read. So you start the start condition. Again, you send the slave address. This is important for every transaction. And you send out 0 after the address to indicate that, hey, slave, number 20, I want to write to you. So the slave will respond by sending an acknowledgement bit. And then the master will send out the actual data. Slave acknowledge. Master will send another byte. Slave acknowledge. And this is another start. Let me see. Yeah, this is another start condition. And then send out slave address. And this again, after that, we're going to do a read operation. So this 1 should be a 1 here to indicate that's a read operation. And the slave will acknowledge. And the because it's a read, so the slave should send out the data. Master acknowledge. And then slave send out another data, another byte, and master acknowledge, and then stop. Yeah, this is some situations where the you can do clock stretching, and also you can you should acknowledge the receiver, whoever receives the data, should acknowledge, and this is mandatory for doing that. If there's no acknowledge, the transfer will be aborted. Clock stretching means the slave device can hold the clock line low, and then the master, because it's on the same wire, so the master knows the clock line is being held low by the slave, so it will slow down the clock. Voltage level translation is important where you have I2C devices operating at different voltage levels. Traditionally, I2C devices are at 5 volts, but newer ones are at 3.3 volts and even becoming lower. So there are several situations, several possible solutions to deal with these devices operating at different levels. One of them is to change a different part and to have a 5-volt tolerant device if you want to really work together on both sides. Because if you put a 5-volt on a 3.3 volt device, and if that 3.3 volts device, the maximum voltage level is not as high as 5, then you are damaging that device. If you happen to have a 3.3 volt device that can tolerate 5 volt, that does not mean that you can connect them directly, because the difference of these two voltage supplies is about 2 volts, and you will possibly have some noise margin, so there will be mismatching logic levels. So by that we mean, for KCSR, you have a voltage level which will be recognized as high for 3.3 volt devices, but at the same time it will be recognized as a low for 5 volt device. So that's where the mismatch happens. So we'll use a solution called voltage level shifter, which can support bidirectional level shifting without using a direction control signal. This is the one example of using logic level shifters. Okay, so coming to our Arduino device, we're showing the Arduino board here. This is the Mega 2560, and we have right here, this is the SDA SCL, these 2 wires that you can connect to hook up a few I2C devices to the Arduino development board. And in our lab too, we will be using a I2C device. That is the MPU 6050